Today we're talking about section 1.7, linear inequalities in one variable. Okay, so unlike equations let's put this on our page so it's not completely blank. How about that? Current page. Okay, so unlike equations that usually have a finite number of solutions or no solutions at all, inequalities often have infinitely many solutions, meaning we have all the solutions, the infinite amount of solutions. For instance, the inequality 2x minus 3 is less than or equal to 5 has infinitely many solutions because there are infinite values of x for which the inequality is true. Take, for examples, these numbers given, 1, 7/2, and 4. If we substitute each one of those values into the inequality, we do indeed see that we get a true statement each time. Working out the algebra there, we're getting -5 is less than or equal to -5, that's true. 4 is less than 5, that's true. And 5 is less than or equal to 5, which is also true. In fact, any real number x that is less than or equal to 4 to make this inequality a true statement. We certainly cannot list all solutions to this inequality individually. So this sentence here says we cannot list all solutions to the inequality individually, right? So for this inequality, all the values that are less than or equal to 5 satisfy that inequality, right? And I mean, again, 4, 3, 2, 1, 0, -1, -2, -3, all the way to negative infinity. And of course, every fraction in between two numbers, right? So like half, third, fourth, all those numbers between 0 and 1, all those are also included. So we can't list every single possible solution. So we have to write our solution in one of two ways, and we'll see down here. Okay. But let's continue on reading. Thus, there are typically three methods used to describe the solution to an inequality. Number one, graph the solution, and that's what you see here. Number two, write the solution in set builder notation, and that's what you see here. And number three, write the solution in interval notation, which you see here. So we can write our solutions to these inequalities in three different ways. We'll do it this way. The inequality 2x minus 3 is less than or equal to 5 is called a linear inequality, okay, because it's linear because we have a first degree polynomial, right? We have the x raised to the first power there. In this section, you learn techniques necessary to solve linear inequalities in one variable. And then our definition, our rigorous definition here, reads, a linear inequality in one variable is an inequality that can be written in the form ax plus b is less than c, where a, b, and c are real numbers and a is not equal to 0. So it's pretty much just like the definition for a linear equation, right? Except the equation would be, equal equation, equal sign. Except it's just a linear inequality, so we substitute an inequality, okay? And then note here, the less than can be, any sort of inequality. Less than, greater than, less than or equal to, or greater than or equal to. Okay, so doing the algebraic manipulation of inequalities, they are the exact same as doing the algebraic manipulation of equalities, right? If I add 3 to one side, I must add 3 to the left side. I'm sorry, to the other side. If I multiply 3 by the left side, I multiply 3 on the right side. Okay, all these 1, 2, and 3. 1, 2, 3. Yeah, 1, 2, and 3. They're all the same. Nothing new there. But 4, it's also nothing new, but it's just one slight difference between this algebraic manipulation and one for an equality. Okay, so we know that if we have some number c and it is less than 0, meaning that if it is a negative number, and if we've got some inequality saying a is less than b, then if we multiply both sides by c, we remember that we have to flip that sign. Okay, and this is only for c being a negative number. Of course, that makes sense. If we multiply an inequality by a negative number, we flip it. We flip the sign. And of course, same can be said down here. If we divide both sides by some negative number, okay, in this particular case, the negative number is c is less than 0, then we flip the sign for division. Okay, and of course, if c is not, if we don't have a negative number, of course we don't change the sign there at all. Okay, so all this is really saying is that for if you multiply by a negative or divide by a negative, you flip the sign, and that's it. Okay. Okay, so solve the inequality, express the answer in set builder notation. Okay, so set builder notation, if you recall, looked like this. So we have to put our solution in a form that kind of looks like that. So let's go ahead and rewrite this essentially. I'm going to go ahead and distribute, get the parentheses out of the way. So this becomes 2 and minus 5x, and then it's going to be a plus 10 is less than, and then 4 times, and then we distribute that 4, so it's 12 minus 8x, and then plus 7. Okay, so we're going to get all the x's on one side and all the constants on the other. So we're going to go ahead and add 8x to both sides. So on the left side, we're going to have a positive 3x. And we're going to move everything to the right side. So we've got the 2 and the 10 makes me 12. So the 12 is going to cancel. So I'm just going to have a 7 on the right side. I'm sorry. Yeah. Yeah, 7. 12. Yeah, sorry. I got mixed up in there. Okay. And then I'm going to divide both sides by 3 to isolate that x variable. So we're going to have x is less than 7/3. Okay. So, but it wants us to write it in set builder notation. So in set builder notation, here's how you do it. You do a little squiggly bracket like this. Okay. Matter of fact, set builder is always going to have the squigglies on both sides. Okay, but we start with this, and then whatever variable we're discussing. So in this particular case, we're discussing x. All right. If this was an a, then we would say a. Okay, but since we're discussing x, we're going to say x. Right, and then we're going to put a vertical line. Okay, and we're going to describe the behavior of x. X, and then that vertical line means such that. So x such that. Well, what is x? What should x be? Well, x should be less than 7/3. Right? And that's the behavior of x. And there it is in set builder notation. Okay, we're going to solve a linear equation, solve the inequality, graph the solution set on a number line, and express the answer in interval notation. Okay, so the first problem we did, we put it in set builder. This one we're going to do graphing and interval. Okay, so the other two. So let's go back and look at what those were again. this is what we just got done doing, put it in Set Builder. Now we're going to put it in interval notation, as well as we're going to graph it. So let's begin by solving. It looks like we can do this, let's see, we're going to add 4x to both sides. So that becomes a negative 5x on the left. Add 3 to both sides, so we're going to have a greater than or equal to, let's try that again, greater than or equal to 10. Okay, all I'm doing now is I'm moving things over in my head. You can obviously write this down if you want to. But anyways, so now we're going to divide both sides by a negative 5. So by dividing by negative 5, what I'm going to do is I'm going to flip that sign. It's going to go from a greater than or equal to a less than or equal to. Well, 10 divided by negative 5 is what? Well, it's negative 2. Okay. All right, so we need to graph this. So let's get us our number line here. So we've got positive infinity over here, negative infinity over here. Looks like we're going to go to the left of negative 2, so I'm going to draw a 0 a little slightly off center over here. So this is going to be a negative 2, negative 1, negative 3, negative 4. Okay, so this graph, if I were to plot this on this number line, I'm saying that that the x value is less than negative 2, less than or equal to negative 2. So less than or equal to negative 2 tells me right now that I'm going to have a dot, a closed dot on negative 2. And it's less than or equal to negative 2, so I'm going to go to the left of negative 2, and I graphed it. Right? That's pretty easy, right? All right, well, what about if we were to put this into interval notation? Okay, so interval notation, if you recall, is essentially looking at where the solution lies on the number line, on the x-axis, on the number line or the x-axis. Okay, all right, well, just looking at this picture, it should be pretty obvious that, it's negative infinity. So we're going to say from negative infinity, and infinities do not get a bracket. Okay, so from negative infinity to what? So if we go from negative infinity on the left, and we go to the right, all the way to negative 2. Okay, all right, but we're also including the number negative 2, so we're going to put a bracket. That's what we did there. That's how we do graphing it and interval notation. So when a linear inequality involves fractions, we begin the solution process in the same way as we would solving linear equations involving fractions. That is, we eliminate the fractions by first multiplying both sides of the inequality by the least common denominator. So as I mentioned before, again, I think it's very rare that you will come to love fractions, but once you get used to them, they are not that bad. So similarly, if we encounter a linear inequality involving decimals, we can eliminate the decimals by multiplying both sides of the inequality by the appropriate power of 10. So before trying example 3, which would be the next one, take a moment to review these two objectives by clicking the links below. Now obviously this is something you can do on your time if you're struggling with this, and of course I do encourage you to take these steps, and if you don't know how to solve these problems, go about the book. Look at what the book's suggesting, click the links, and then refresh yourself. Okay, but obviously, in this lecture, we will not be doing that. Okay, one moment. Okay, I'm back. All right, so we've got we got fractions and we've got decimals. Decimals, and nobody ever really whines about decimals, do they? All right. So, anyways, we're gonna start with the fraction. We're just gonna set these problems up like we did the first two problems. We're not gonna go all the way. Okay. So for A, we've got 1 minus 4w over 5 minus w over 2 is less than or equal to negative 5. Okay, so what do I need to do to this problem? Well, I look at my denominators, and it looks like my denominators are, my least common denominator would be 10. Okay. I can't remember if I said it to this class or another class, but you can, and there's nothing wrong with this, you can just say, okay, I'm going to multiply this left side by 10, and I'm going to multiply this right side by 10, okay? And be done with it. Or, well, not be done with it, but and then proceed algebraically that way. And there's nothing wrong with that, okay? But if I'm multiplying the left side by 10, and I'm multiplying the right side by 10, I'm essentially multiplying this entire problem by 10, right? So I usually write it like this. Okay. Well, if I multiply the entire problem by 10, okay, distribute here. So the 10 over 5 turns into 2. So we've got a 2 times 1 minus 4. We're just getting dots there. Okay, let's fix that 4. 4w. Okay. And then we've got a minus 5w. And it's less than or equal to negative 50. Okay. And then from here, we can proceed like we have been. Let's close our parentheses. We can proceed like we have been on the previous two examples. Okay, so B. All right, so B is a decimal. So we talked about decimals very briefly before, and so if we have these decimals, what we're looking for is essentially the highest place, the highest place decimal. So you have your tenths, hundredths, thousandths, so on and so forth. So we're looking for your largest of those. So the first term we have a tenth, the second term nothing, third term a tenth, and the fourth term we are in the hundredths. Okay, so what I'm going to do is multiply this entire problem by 100. Now, realistically, I guess you could just simply put this into your calculator and subtract 3.45 from both sides, and you get what 0.25. And this, honestly, that's probably easier. But for the sake of the way the book probably wants us to do it, we're going to multiply by 100. So I didn't leave myself too much room here, so we're going to multiply the entire problem by 100. Probably not going to show up on the notes, but I don't know if you guys even look at the notes anyways. So we've got 370y minus 600 is greater than 610 plus 345y. Okay. And then proceed like we did in the first two. Ooh, a 3-part. Okay, so now we're getting a little crazy with our inequalities. Somebody's going to have to slow these guys down. Okay, I don't know if I should have snipped that, but we're going to read it anyways. So the weight of a laptop computer depends on several factors, including the size of the monitor, the thickness, the type of battery, and the type of internal hard drive. The weight of a typical 14-inch laptop varies between 1.2 and 8.4 pounds. Good grief. The weight can be expressed using the following three-part inequality. So what we would do if we wanted to express this weight is we would say, okay, so the weight has got to be between 1.2 and 8.4. Okay, that's where it says this at the average, right? Or typical, the weight of a typical, so the average one, right? So we would write the inequality like this, where W is the weight of the laptop. Notice that the variable W is between two inequalities. The technique to use when solving three-part inequalities is simply The technique to use when solving three-part inequalities is to simplify until the variable is sandwiched in the middle, as in our example. Okay, so I didn't do anybody any favors by getting tongue-tied and being illiterate there, but I can explain example 4 a lot better than I read that paragraph. So let's do that. So solving a three-part inequality. So we are going to, for the sake of this, we're just going to go ahead and we don't need to rewrite it. Okay, so looking at this inequality, okay, we're used to having two sides of an equation, a left side and a right side. Okay, well now we're going to have three sides, but the same rule applies. So the same rule that we saw on the inequality pages. Let's see here. The same rules that we did here will apply to a three-sided inequality. So what I mean by that is this. So if I'm looking at this middle term here, how would I just in a vacuum get rid of that 3? Well, I would multiply by 3, right? So that's what I'm going to do. I'm going to multiply this entire three-part inequality by 3. Guess I can't erase that. Good talk. Okay. So I'm going to erase it. I'm going to multiply it by 3. So if I multiply -2 by 3, I get a -6. Okay. If I multiply the inside part by -3, well, that gets rid of that denominator. So we're just what we're wanting. 2 minus 4x. Then I multiply the 5 by 3. I've got a 15. Okay. We're not done yet though. So now what we're going to have to do is looks like we're going to have to divide by, or I'm sorry, subtract by 2, okay? Because we want to get this inside term, we want to get the x by itself, just like this up here. Okay, so we're going to subtract 2 from all sides, so we're going to have a -8 is less than or equal to -4. My 4 just are not on today. Minus 4x, and then we subtract 2, so less than 13. Okay. All right. Well, we're not done, obviously, because we have to isolate that x variable. So what we're going to do is we're going to divide all three sides, by a -4. Okay. So in doing so, what we're going to do is we're going to flip the sign. Okay. So we divide -8 by -4. We're going to have a +2. We're going to flip this sign, greater than or equal to x, or greater than or equal to. All right, well, if I divide -4 by -4, the whole point of doing that was to get that x there. We flip this sign as well, and we get 13 over, oh, it should be -13. Okay, so now the 3's are not my fault. For some reason, this program doesn't like it when I write 3's a little tiny there. Okay. All right. So we wrote it like this. Now, I don't know if it's typical or if it says it in this textbook, but when we write inequalities, we typically want them, saying less than. Okay. So we're going to rewrite this and we're going to just flip everything to where we have less thans. Okay. So we've got a -13 over 4 is less than x, which is less than or equal to 2. Okay. The reason why is because when we read number lines, you know, we read number lines from left to right, right? Well, that's what we do here with inequalities as well. We read from left to right. We have negative 13 over 4. We know that's on the left, and we know that 2 is indeed greater than negative 13 over 4. Okay, so since we read number lines left to right, we set up our three-part inequalities left to right as well. Okay. So anyways, it says graph the solution, let's set our number line, write and set builder notation and interval. Okay, so we're doing all the things here. So let's begin. We'll first do number line. Okay, so it looks like I need to put maybe 0 here. We'll offset. Okay, and we're just going to do -2, -4, so we don't congest it that much. Okay. All right, so if I wanted to graph this, it's going from -2, so from +2, so we are going to fill that in. That is a nice giant circle. Let's see if we can make it a little bit smaller. Probably same size, huh? Okay, so we're going from there. All right, so negative 13 over 4. So negative 13 fourths. All right, well that is essentially what? -3 1/4, pretty much, right? Okay, so -3 1/4 would be about right here-ish. Okay, so if I drew this on a number line, it would look something like that. Okay. All right, so that takes care of that. So next we're going to deal with, we're going to put interval notation underneath it, okay? Because I feel like looking at a graph, we can easily see the interval notation. Well, the interval notation here, it looks like we are not including negative 13 fourths, okay? But we are going from negative 13 fourths. So when I say not including, that's because it is just a less than. It's not less than or equal to. So we put a parentheses there. Excuse me. And then we're going to 2, okay? But since we are including it, it is less than or equal to, we're going to put a bracket. Okay. All right, and then my favorite, last but not least, this is my favorite, and the reason why is because once you can wrap your head around how you write it, it's essentially just rewriting this. And that's all it is, okay? So like I said from the get-go, what we're going to do is we're going to say, okay, so we're going to put the squiggle like this. I used to have a classmate. He's like this. Actually, that actually looks good. He would go like that. It would just be literally a squiggle. But anyways, that's a curly brace. So curly brace there. All right, and then again, the variable we're using is x. So we're gonna say x, and then such that. Okay, well, what is x? Okay, well, again, we're just gonna rewrite this. Okay, x is going to be between negative 13 fourths, which is less than x, which is less than or equal to +2. And that's it. So we solved it, we graphed it, we put it in interval notation, and we put it in set builder notation. Man, I'm ready for the weather to change. I'm tired of being hot. Okay, so we'll snip all this. Okay. So, reading from the top here, we've got, before we solve compound inequalities, it must be a good idea to review the concept of the intersection and union of sets referred to section R1. So this is the very first review section. in this text. So if you need to, please go back and do it, guys. You are budding scholars. I understand the need to maybe get through these assignments really quickly. You know, you have things to do, but it will serve you well to fully understand what you're doing. And if you spend a little time now, that's a lot of time later you don't have to work on it. Okay, so just a little pro tip: please take the time to actually go back and review something that you do not remember or you're not really fresh on. Okay. So, a compound inequality consists of two inequalities that are joined together using the words and, or, right? And, or. Two compound inequalities are shown below. So, whereas A, we're saying x plus 2 is less than 5, and 3x is greater than or equal to negative 6. X plus 3 is less than or equal to 1, or 2x minus 5 is greater than 7. Okay, so a number is a solution to a compound inequality involving and is if that number is a solution to both inequalities. So if we use the word and, it's going to be both inequalities. It's going to be a solution to both inequalities. Okay, and we would use the intersection symbol. In A above, the number 2 is a solution to both inequalities, thus 2 is a solution to the compound inequality. To find all solutions to a compound inequality involving the word and, we first find the individual solutions set to each inequality. We then determine the intersection of the individual solution sets. Okay, so I'm actually going to not read the rest of this, mainly because I feel like a lot of times what's being wrote is very helpful. And I'm not saying it's not helpful, but I do feel like it's a lot more helpful if I actually do it, right? So what I'm going to do is I'm going to I'm not even going to look at the guideline over there. I'm going to jump straight into this example, all right? But before I do, I want to impart this real quick. If we see an and, okay, then we're going to put this symbol. If we see or, then we're going to put this symbol. And of course, we know at least this is how I was taught, was this U, right, means union, right? The union of two sets, right, which correspond with or. Okay, so if we see and, it's an upside down U. If we see or, it is just strictly, a U, right? So solve the compound inequality. What we're going to do is we're going to write this as two different equations, and they are obviously, but we're going to write one over here on the left. So 2x minus 7 is less than negative 1, and then we've got a 3x plus 5 is greater than or equal to 3. Okay. So I'm just going to solve them individually. So looks like I can add 7 to both sides on the left. So we've got an x is less than 3. Sorry. And then we're going to subtract 2 from both sides here, and we've got an x. I'm sorry, subtract 5 from both sides, and we end up with a 2. So x is greater than or equal to 2/3. Okay. All right, so I did that. I have my two problems. Now, to write the solution set, okay, this particular problem has an and. Okay, so I'm going to write one of these in between for my. I'm not going to write one of those, I guess. So that's not a hard and fast rule, and we'll see why in here in a moment. But I won't be using the union. Is my point. Okay. Okay, so let's put this on a number line, because I feel like if we put this on a number line, it will be a lot easier to see. Now, there will be many among you that can probably just do this in your head, and that's fine. So it looks like we're going to need to go to not far. that's supposed to be a negative. We'll do so we're just going to call these, we're just going to go the even numbers here, 2, 4, and then negative 2. And I'm actually going to rewrite this. I'm going to put it in a different color because it really drives the point home if I do that. So let's do that again. So what was it? We said it was, all right, so the problem was 3x plus 5 is greater than or equal to 3. We said that x is greater than or equal to negative 2/3. Okay, so I really want to drive this point home, and we'll see why in a second. So x is less than 3. All right, so what we're going to do is we're going to put an open circle here at 3, and we're going to be going all the way to negative infinity. Okay, and x is greater than or equal to negative 2/3. So negative 2/3, you know, that's almost to a negative 1, right? But it's not quite there. So we're going to put a closed circle here. Okay, and we're going all the way to infinity there. Okay, so this problem reads and, again, the and up here. Okay, so it's saying, okay, so and means that it is in both. It is in both solution sets. So it will be the intersection, So where do these intervals intersect? So if you didn't want to draw this, or if you know, that's fine, because you could probably, you know, picture this and do this in your head. But if you're just starting out, I do encourage you to draw it because it does make it a lot easier to follow along with. Okay, so what we're going to do is we're going to say, okay, so where does the blue line and the green line, where do they overlap one another? Okay, well, they don't overlap anywhere here or anywhere here. Okay, I mean, to the left is just blue, to the right is just green. Where they do overlap, though, is from here to here, right? So it will be from the negative 2/3, and we're going to include negative 2/3, okay, because the green line does go to negative 2/3, and the blue line also goes straight through negative 2/3, so we do include it. Okay, and where does this go to? Okay, well, this goes all the way to, well, it looks like it goes to right here. Okay, but we do have a slight problem. While the green line does include 3, it goes all the way to 3, all the way through 3. The blue line doesn't. It goes to 2.99999999999, right? So what we're going to do is we're going to write the number 3, because we're not going to write 2.999999999, are we? Instead, we're just going to write the number 3 and put a parentheses. And that's it. We officially did this particular compound inequality using the word and I'm pretty sure we're going to be using the word or next. Yep, and there's the or. Okay, so solve the compound inequality. 1 minus 3x is greater than or equal to 7, or 3x plus 4 is greater than 7. Okay, so we have the word or there. Okay, so or tells us that we're going to be using, you know, the idea of the union. Okay, so once again, let's write this out. So 1 minus 3x looks like we subtract 1 from both sides. We got a 6. So we've got a divide both sides by negative 3x. We've got an x, and then we're going to flip the sign. So it becomes a less than or equal to 2. You know what? Let's actually write the whole problem, just like on the previous page. And then over here was 3x plus 4 and 7. Okay. Excuse me. So the blue, like I said, we'd subtract 1 from both sides. So we'd have a negative 3x is greater than or equal to positive 6. And then we would divide both sides by negative 3. So in doing so, what we do is we would divide both sides by -3. We would have to flip this sign, and then we'd have a -2. And then over on the right side, that's pretty easy, right? Subtract 4 from both sides, divide by 3, so we've got x is greater than just 1. Okay, so same as before, let's draw our number line. Okay, so this looks like we can probably just be right in the middle. So the -2, so we're saying x is strictly less, or is less than or equal to -2. So I'm going to go over here to -2, okay, and it's all the values that are less than or equal to -2, so we're looking at that. Okay. The right side, x is greater than 1, so we're going to start here at +1. It's going to be an open circle, okay, because we're not including 1, and we're going all the way to the end there. Okay, so on the previous one we had the and, it was where they intersected, okay? On the previous one, the and intersected, we think of that and we say, okay, so where do these two collide? Where do they intersect at, okay? This one, we're not looking for an intersection. We're just looking for, well, where in the world does it exist, right? So it exists everywhere where you see blue, and it exists everywhere where you see green. So if I were to write this in interval notation, if I were to write the blue here, okay, it looks like it's going from -infinity all the way to -2. We're including the -2, okay? And this right side here, the green one, all right, it looks like we're going from 1, but we're not including 1, all the way to +infinity, okay? And this is where the union comes in. We just slap a little u in there, okay? So again, all I did was just write what that is. I write what that was. And then since it was an or, that's how I know it is a union. Let's see if I can write it. Hey, that's a good one. That's a good one right there. All right, so that's it. So we did an and, we did an or. What do we have next? That's interesting. Okay, so this would be a special case you might get. It is a tricky one. Oh, that's not what I wanted. All right, so let us begin here. Let's just go ahead and begin like we did before. So we're going to write the inequality. So 3x minus 1 is less than -7. And then over here we've got a, oh man, my 4s. 4x plus 1 is greater than 9. If I solve these inequalities, is that the same as a previous problem? No, close though. Okay, so if I subtract, or if I add 1 from both sides and divide by 3, I've got x is less than -2. And over here on the right side, I've got, I subtract 1 from both sides, divide by 4, so I've got x is greater than a +2. Okay. I didn't actually emphasize what the problem was, so let me go back and do that because that's important here. So it says solve 3x minus 1 is less than -7, and okay, that and is telling me we're going to have an intersection. Okay, so we're going to be looking for where these two overlap on a number line. So let's draw the number line. And of course, some of you are probably screaming at me. Actually, no, but none of you are, right? But for some of you are probably like, well, it doesn't exist, or they don't intercept on a number line. And that's fine. But again, I think it would be good for many of you that are, just kind of new to this to draw it on a number line. Let's go that far. So the -2, so we're saying x is less than -2, so we're going to have an open circle here at -2, and we're going all the way to negative infinity. And then we have an open circle here at positive 2, and we're going all the way to infinity. Okay, so keep in mind that this is and, so this means intersection. So I would ask myself, okay, so where did these two number lines, where does the blue and the green intersect? Okay, well, they don't, right? Obviously, they do not overlap one another. So what we would say is that the solution set here, okay, is the empty set, right? And that's it. And I guess now would be a great time to put this out. And some of you may have done it in the past. Whatever, it doesn't bother me one way or the other. But sometimes if people think, they see this empty set 0. Okay. Now, if you want to in your day-to-day life say, hey man, you owe me $20. Whatever, I don't care. Write your circles like that. Or write your zeros like that. All right. But in a mathematical context, all right, if we're talking about math solutions, all right, if you write a 0 like this, that means empty set. Okay, it has a specific name to it, and I say that because I remember signing a thing for an athlete, because I have to sign these forms that, hey, yeah, he's been in class, things like that, and I was one of the last of this particular student's instructors to sign, and he hasn't missed any days in class, right? So the first instructor that signed it, says he's missed 0 days, 0 days of class. The next instructor to sign it is like, you know what, I'm gonna do it too. And then next one says, I'm gonna do it too. And then I'm like, and then it's my turn. I'm like, well, he's missed 0 days. Okay. Again, it's not a big deal. Whatever. You do what you want to do. But in a mathematical context, that line to the 0 does mean empty set. All right. So the strategy for application problems. Not there. Sherman, get out of here. You'll be doing some nice fancy word problems on your homework, and this would be the strategy for that. All right. Obviously, you can take these algorithms, 1 through 6, that's fine. But again, just like I said before, baking a sandwich, you don't go, step 1, step 2, step 3, to just kind of really understand the procedure, what you need to do, and then solve from there. This concludes the lecture.